Hello, and welcome to Empowered Learning. This video will be about calculating the volumes of solids using cross-sections. And when we say using cross-sections, we're actually talking about three different methods. One method is by stacking or slicing. Another method is by doing what's called the disc method. And the last one is called the washer method. So whenever we talk about the slicing or stacking method, what we're actually doing is we're imagining that our solid can be sort of sliced up into very thin wafers of whatever area that it sort of coincides or sort of it represents within that particular slice. And then we take a bunch of those very thin wafers of whatever area that is, and we stack them. And we'll either stack them horizontally or stack them vertically. For the disc and washer methods, how we're actually forming these solids to create the volume is we're taking an area and we're spinning it about some horizontal or vertical axis. And so we're going to stay in this particular video just dealing with things that are spinning about the x-axis or about the y-axis or some other vertical or horizontal line. We won't be getting into solids being spun around, let's say, a line that has a positive slope or a negative slope or around some parabola. We won't be doing anything in that regard. So let's go ahead and get started here. So again, I'll just read. The purpose of this section is to learn how to calculate the volume of objects that are not normal geometric shapes that are in three dimensions, such as cylinders, circular cylinders, rectangular boxes, spheres, etc. Okay. Now we're going to use calculus to do this, and basically we'll use integration. And so what we will essentially be using the integration for is adding up a bunch of very small areas of, I'll say, adding up a very large amount of areas that have a very small thickness. I want to say it like that. And so to sort of illustrate what I'm talking about here, we'll go to this first picture here. And you'll see in this picture, this particular solid kind of looks like a loaf of bread. So I'm just going to use that as an example. And so the pink slice that you see in here is sort of like saying, hey, well, let's cut the bread right there. Okay. And then from this particular point here, let me put that down here. So let's say from here, it's not working right. Okay, here we go. So from here, which is the x of I minus 1 to here, that would be what's considered the thickness of this particular piece of bread. Okay, and if we put it into, or we slice up this piece of bread into those thicknesses, then what you see here is a bunch of slices of bread that have the same thickness there. Okay. Now, of course, with integration, the idea is just like with area under the curve, and we talked about figuring out what the area under the curve of a particular function is by taking a bunch of rectangles, taking those areas of thickness dx and adding them together. We're doing the same kind of thing here with the volume. And so what we're doing here is we're going to take a volume that has a side of area whatever, and then of course area times thickness is going to give us volume. And so that thickness is described by the difference in between the x of I minus 1 that's here and the x of I that's here. Okay. And so if we can characterize the area of, let's say, the slice of this bread, then what we can do is just add a bunch of those very thin slices together to come up with what the volume should be. So that's essentially what this particular picture talks about here. And so we want to do the following to calculate this, I guess, loaf of bread or the volume of it. Okay. So the first thing is we want to find the area of one side of the slice of bread from the loaf. The second thing is we want to multiply this area of this slice of bread by the thickness, delta x, to find the volume of the slice of bread. And number 3, the last thing that we want to do is multiply the volume of the single slice of bread by the number of total slices in between, let's say, x equals a and b. And of course, if we refer to this picture here, we're talking about a being right here, being b right here, or in this one over here, a being right there, b being there. Now, one of the things that we're assuming here is that each slice of the bread that we saw back in the picture on the previous page has equal thickness, okay? And so we'll calculate the volumes of unconventional shapes and figures much in the same way we just did this for the loaf of bread, okay? And so in general, we want to say let S be some solid, and we want to say that it lies in between some x value A and another x value B. And we say that the cross-sectional area S is in plane P sub x, and P sub x is perpendicular to the x-axis. And we're going to name that area A sub x. Now, I know that's a mathematical jargon here, so I'm going to go back to the first page and just basically explain what this particular sentence is actually trying to describe in words here. Okay, so I'm just going to skip back for a second. So on this page here, if you look at the pink area that's there, that is considered to be the area A sub x. Okay, so area characterized in terms of x, and we know that this particular area is perpendicular to the x-axis here, okay? Because of course, if this particular area that's right here, if it was actually slicing the x-axis, it would do it perpendicularly, okay? And so we're just saying that the plane that's formed by this particular slice of bread of thickness dx, we're just labeling that P sub x, okay? And so we have, let's say, the bread that's like this. We name that A sub x. And of course, if we kind of turn the bread on its side, like how we have here, that thickness there would be, let me get rid of this, all this. This thickness here would be the delta x that we're talking about, okay? Or if we look at it infinitesimally, it will be dx. All right, so now that we sort of understand what this sentence I have outlined says, the only other thing that we need to understand here is that if we are able to take the area that we're talking about and model it as a continuous function, then of course we can use integration to be able to figure out what is going to be the sum of all of the volumes going from x equals a to x equals b. And so of course this is going to be some volume v sub I, because of course we got area here times the thickness, and that will give us what our volume is. So we're doing a sum of volumes here, because we know of course volume is just length times width times height. So if you want to think of it one way, here the length times width is what the area would be if we're thinking about this in terms of squares, and the thickness here would be the height, okay? Or we could write it like this, where the thickness could be interpreted as the width and the area would be the length and the height, if we're thinking about rectangles. So my point here is that we just understand that what's inside of here is just expressing the volume for a very thin slice, and the summation here is saying we need to add n number of slices together. And of course, when we add the limit notation along with the summation here, that combines together to be the infinite sum, or what we know as an integral sign. And of course, that'll be from A to B. And so this is essentially the formula that we use, okay? Now, the part that's a little challenging is understanding how do we actually characterize this area, okay? And so depending upon how the the solid is actually formed, that's going to determine, again, whether we're going to use the slicing or stacking method, whether we're going to use the disk method or the washer method. All right, so before we get into sort of the nitty-gritty of it, just showing you here the volume, we could rewrite this particular portion here as just being a sum of all these different areas. And of course, depending upon what sample X value we want to consider, that will let us know what corresponding area with what small thickness is at those particular places, and we just add them up. All right, so the steps for calculating the volume A sub x times the infinitesimal thickness d of x of a solid starts off with first sketching a solid and a sample of the cross section with the thickness of delta x, so that we can kind of get an idea of what it is that we're dealing with. And then we want to find a formula to characterize the area of just the cross section. Okay, and then from there we want to determine what the limits of integration will be. And so sometimes if we have area that's formed by like an area in between two curves, or sometimes we're explicitly told to say, hey, look at this area from this x value to that x value, and we only have one function that we're considering, that would determine what the limits of integration would be. And remember that a of x must be a continuous function on a closed interval from a to b. And then, of course, we would just integrate whatever that area is from x equals a to x equals b to find the volume. Okay. Now, I've mentioned this before, but I said based upon how the particular solid is formed, that depends upon the strategy in which we use to try to calculate the volume. And in particular, if we use the method of slicing, as I refer to here, what we're actually saying is that we can form that area by either stacking a bunch of areas, whatever the area may be characterized to be, either horizontally or vertically. Okay, and of course, if we stack those areas of thickness delta x, and we do a limit of the summation of all those volumes, then of course we're going to get what the actual volume is. Okay, now, whenever we are taking some area and rotating it about an axis, in those cases, we would use either the disk or washer method. Okay, so now what we're going to go through is what we would need to look at if we are going to deal with what we call non-solids of revolution, which deals with this case. And then for this case, this would be solids of revolution. So we're going to deal with the strategies for how to go about trying to figure out the volume for each of these cases. All right, so whenever we know that we're dealing with a particular solid that has an area, a sample area that's going to be something that we use for slicing, we'll know that because it won't look like a disk or a washer. And so for those of you that aren't familiar with those terms, a disk just looks like a circle. Of course, everything's filled in. A washer would be like this, where of course only the area here is filled in, and we have a gap, kind of like a donut. Okay. So we know that whenever we have shapes that sort of don't either characterize a disk or a washer, then we know that we have to do solids of non-revolution type strategies, which is basically the slicing or stacking. Okay, and so of course our formula would depend upon the actual shape of the cross-sectional area, and we often may need to do some geometric relationships like similar triangles and such to be able to help us solve the problem. And so of course, if you're able to characterize the area that you're talking about in terms of your variable x, then you integrate with respect to x. And if you can characterize your area in terms of your variable y, then you integrate with respect to y. Now, whenever we are considering solids that are formed by taking an area and rotating it about a vertical or horizontal axis, then that's what we call solids of revolution. And of course, we'll know that because we'll be told, hey, the area is formed by taking this shape and rotating it about this particular line. Like let's say like x equals 2 or y equals -5 or either the x or y axis, something like that. Whenever we use the disk method, what we're basically doing is doing a variation of a theme of the area of a circle. So of course we know the area of a circle is just pi r squared. And so if you notice here, this looks very similar to that. So what we have to do is be able to figure out what is going to be the radius of the disk itself, either defined in terms of x or in terms of y. And of course, that needs to be a continuous function. Okay. So we know that if the radius of the disk is written in terms of y and the line or axis of rotation is vertical, then of course we'll be dealing with it that way. Okay. So in other words, if is written in terms of y, then of course the axis of rotation itself is vertical. If it's written in terms of x, then we know the axis of rotation is horizontal. So let's say if I was taking an area here, and I'm going to rotate it with respect to x here, then of course I know that, of course, axis of rotation is horizontal. So let's say I'm doing it with respect to the x-axis here. However, if I want to take the same shape and I want to rotate it with respect to y, then of course, rotate it about the y-axis, then of course the axis of rotation is indeed going to be vertical. If we use the washer method, we're going to know that we need to use the washer method, of course, if we're told that the area is going to be rotated about an axis. But in addition to that, there's going to be a gap in between the actual area that we're talking about and the axis of rotation. And so that's very important to know. So that's one thing that I do want to mention here. So I'm going to erase this. And so one of the things that we know for disk method, there is no gap in between area and axis of rotation. Whereas for the washer method, there is a gap that exists between area and axis of rotation. Okay? And so when we are looking here, we see that we're doing the difference in between the area of a circle, where the outer radius is big R of x and the little radius is little r of x. Okay? And we still should be able to characterize a radius as a continuous function if we're going to calculate the volumes this way. And finally, before we get to doing some of the examples here, we see that, again, if we're going to characterize the radius as a function with respect to y, then of course the axis of rotation is vertical. And if we're able to characterize the radius with respect to x, then we know that the axis of rotation is horizontal. Okay? So next what we'll do is get into some doing some non-solid of revolution examples and then solids of revolution examples.